Good afternoon, everybody. We're the AME plasma filtration team. I'm Nato.
Cool.
Denzel.
John, and Jake. All right, a little bit behind the motivation of our project. Currently there's no specific filtration device in the AME shop for plasma cutting. Right now they just have a welding fume extractor, which has a poor capture velocity, which leads to a lot of inefficiencies. This couple semesters we're going to look to improve those efficiencies and make sure there's clean air in the AME shop. Since it's a university facility, obviously we want there to be clean air for the students and faculties to work and make sure that dirty air isn't leading to illnesses like a dry throat, runny nose, or lung issues.
So here we have the plasma cutter at the shop. For those that are not familiar with the plasma cutter, it's just compressed gas that shoots down, creating an arc that cuts through different types of metal. As you can see here, it gets shot down and then it disperses to the sides and yeah. So a little bit of an introduction. So the plasma cutter runs for about 8 to 10 hours. It varies depending on the lab schedules and different projects in the school. So our task is to come up with a filtration device that's going to capture and prevent this dust and particulates around the plasma cutter area. We are aiming to recirculate the air into the shop instead of venting it out of the building. Also, we got to be within reasonable budget and size since the AME shop's going to get a redesign in a few years. And overall, the goal is to just improve the air quality around the plasma cutter and the shop consequently.
These are some of the initial requirements set to us by Tyler, our shop manager there. First of all, the system needs to filter out particulates and fumes and recirculate it, as he mentioned before. Can't vent out of the building. It needs to be autonomous. What we mean by that is little to no human interaction. So when the plasma table turns on, the filtration system turns on also. It needs to be movable. These are for a couple different things. If he needs to bring in any big equipment from the side door, it needs to be movable a little bit. And when they expand the shop, they're going to move the plasma table to a different spot. So it needs to be movable for that. Also, another constraint is no humidity added to the shop. So this kind of cuts down some of our filtration options, which we'll get into later. And no buildup of thermite because the two materials we cut are steel and aluminum, and a certain percentage of each of those mixed together creates thermite. And that's a big no-no. And it also has to follow OSHA standards.
These are all goals and justifications. Our main goal is to reduce the airborne metal particulates in the plasma cutting area by 75% for the air quality test. Our filtration system also aims to save money by recirculating that clean air in the shop instead of venting out that dirty air. We'll show some calculations later as to why. The current welding fume extractor has a poor capture velocity. We also want to create a safer environment because that's very important for universities. We want it to be movable since a lot of them are not, and we want to maximize our space by minimizing our footprint.
Okay, so our group had a pretty neat opportunity to participate in the I-Corps program, which for those of you that aren't familiar with it, it's basically a program that allows you to do real life customer interviews. So that way you can kind of identify your market better and get the overall knowledge for pains and gains when developing your product. Our group had the opportunity to do 30 in-person, over the phone, and Zoom customer interviews, which these were with engineering faculty, campus faculty, some facility managers, warehouse managers, and then some HVAC consultants and entrepreneur advisors, which they all gave us insight on how to effectively interview our customers and gave us some good overall feedback. Which one of the main things we learned was when we started our project, we went into it with a kind of a broad view on, oh, we're going to sell our filtration device to every plasma cutting table out there, which through the first couple, we realized this was not the way to think about it. We had to kind of look at our market from more of a niche view, which was just plasma cutters on campuses and makerspace areas. just because they're not run as much and they're not as much industrialized, and they emphasize safety. So that's kind of why we limited our market to that. Another big thing we learned was that not necessarily, we don't have to like reinvent the wheel. We don't have to come up with like a crazy idea that's never been out there. We just got to look at the ones that are already out there and improve on their weaknesses, which one of the weaknesses out there was a downdraft table. They have some limitations with the doors because they get kind of jammed sometimes, is what we heard from a couple of customers out there. And then another big thing was just hide the safety devices that are in our design, because they give the user that like assurance that our product's safe. It's going to help keep their workers and students safe and create a better atmosphere in the shops. And also another big thing we learned was that every plasma cutter table is got a different environment. This means like some of them are going to be indoor, some of them might be outdoor. They're going to cut different materials, whether it's aluminum, steel, or something else, and the thickness of the material is going to be different too, which is just going to affect how much the fumes and particulates come off. And then lastly, the placement's very important, because Cole was talking about it earlier. Where in the AME shop, it's kind of limited in the corner of how far we can extend our device. So one of the big things we had to do was our box is going to go more vertical than horizontal, just to save on space. And it's just something that it's important for the future when we're trying to market the product, that we make it so that way we can put this filtration device in other spaces that are going to be different from the one here.
So here we got our Gantt chart for the first semester with a bunch of different categories and the dates, as you can see. We spent a lot of time on researching in the first portion of the semester. We also had the CAD drawing, budget, the filtration system, different presentations, and we're right now at the senior design conference presentation. Beautiful slide. Here we got the second semester, so not as many categories. We got our CDR coming up, which is going to be pretty important, and then a few progress reviews, the demo, the engineering expo, and finally the delivery of our final project to the sponsor.
All right, so looking at the design concepts and ideas aspect, there's two ways to enter your product into a niche market, and that's by offering the same value product at a lower cost, or offering in a more premium product at a premium price. This led us into looking at what's already out there, and that's a welding fume extractor. The basic concept is you have a inlet that you put over the plasma cutter head, which sucks in the particulates when cutting, and then ducts it out to a box concept, which has your fan or filter placement, and it either gets exhausted outside the building or gets recirculated into the environment. And then it's what's known and what's already out there, so we're going to look more into how to better the product and how to go from there.
So this is our first design presentation. Here we went with an overhead extractor type concept as the basis for our ideas. We had some considerations that came with that as to how can we collect more particulates than the designs that already exist. We also noticed a huge flaw in this design, and it was that the compressed air from the cutter shoots down and then disperses. So we considered going below the table with the hood. And we also considered, what if we could capture these fumes before?
This led us into our first and biggest decision matrix, which was figuring out if the plasma cutter nozzle should be located above or below the table. Above the table lacked in aspects of CFM, which led to poor efficiency and capture velocity of the design. So doing the calculation for the weighted score for the decision matrix below the table won, and this ultimately ended the debate, the back and forth debate of whether we should go above or below, and led us into our next design. Our schematic shows that this is a under the table view of the plasma cutter. The nozzle is attached to the table. It's on the x-axis and not doesn't move on the y-axis to help with the electronic aspects of that. So the nozzle is on the left side, and then the particulates will get ducted to a box concept Going further into the slides, we'll look at how to the more specific components of the project, like capture velocity, filters, and fans, and what's inside the box.
Speaking of capture velocity, I'm not sure if you guys know what that is, but it's the velocity necessary to capture or basically grab the particulate and fumes out of the air and move it through the air. On the right side of the screen, you can see an equation and a little figure there. This was grabbed from the ACGIH Industrial Ventilation book. I think it's 1998 version. And you can basically view that figure there upside down and the bench or the floor as our actual plasma table and the material. And so we use that equation there to find our CFM rate for our fan. And based on the video seen before, the width of the fumes is about 2 feet in diameter roughly, or the length it'll be from our nozzle is going to be a max of 2 feet. So we use that at 100 feet per minute. Also that industrial ventilation book also specifies the capture velocity for welding fumes, and that's 100 to 200 feet per minute. So we use the 100 feet per minute at 2 feet away and that'll equal 2,400 CFM for our fan size. And using that CFM, we can then verify our actual capture velocity with our nozzle. We expect the fumes to actually only be about 1.5 feet away from our nozzle. And that'll give us, with that 2,400 CFM, 157 feet per minute. So right in that range of 100 to 200 feet per minute. And then our actual nozzle will only be about 6 inches away from the actual cutter head and the fume generation. And that will actually give us 450 feet per minute. So plenty of capture velocity. And this leads into our third decision matrix, which is our filtration. We kind of had 4 different concepts initially. 2 of them were water-based, that 5-gallon bucket of water, and mist. Kind of threw those right out the window right away just because of humidity reasons. So those are gone. And we got left with 2 of them, regular filtration or paper filtration. So if you think of a furnace filter, that's your paper filter. Or electrostatic filtration, which is basically charging the ions in the filter to attract the ions of the particulate and fumes. The difference between those that came out and what made the paper filter win out was cost and safety reasons, but mainly that. So we kind of lean towards the paper filters, and going from there, paper filters are rated on a MERV scale. If you don't know what MERV is, it's an ASHRAE rating that they created. It is the minimum efficiency rating value, and they go from 5 to 19, I want to say. And on here, it just specifies a couple of different ones. We went for we have 2 different filters. We have our final filter, which will be a HEPA filter, and we have a pre-filter, which we need to will be a MERV 15. Listed there is a MERV 13. The reason we chose a MERV 13 is because it actually filters out the smoke, and smoke actually will clog up a HEPA filter very, very fast, and a HEPA filter is very expensive. And a HEPA filter is equivalent to a MERV 17 roughly. Actually, it's a little bit better, but it's basically equivalent to that.
This is our second design presentation. This is where we put more thought into what actually goes into the box. Our components include a spark cooling system, like a spark cooler or mesh filter, our pre-filter, fan, and final filter. Here we realized that we had to take special consideration for the placement of the fan and filter to find the balance between performance and longevity. We also had to consider the size, shape, order, cost, flaws, and strengths of our system holistically. And we also had to consider anything that we may have overlooked. This is our current design. Here you can see we switch from a horizontal concept to a vertical concept. Here it uses most of the same components with some added components. Starting from the furthest point to my right, you can see that we have a chain and sprocket actuating mechanism. That's what will move our nozzle. These 2 components will be under the table. So this will move our nozzle back and forth about 6 inches from the cutting head to capture those fumes. After that, we have our flex duct, which is just the ducting material that stretches and compresses to move along with the nozzle. The air flows into that, and then into the mesh filter on this side here, which would help cool any sparks and the air that comes into the system. Then we have some turning vanes that will direct that air at a 90-degree angle up into our pre-filter, which then flows into our main filter. And finally, that's exhausted out of the system by a fan at a 45-degree angle upward. If you also look, you can see we have some electrical components on it there with a screen, a Raspberry Pi, and the Arduino board. Those will help actuate our mechanism and also give us information on our pressure drop. Also here you can see that we have this comparison of the average height from eye level compared to our system. Here we have it at about 5'4", and our system would be about 6 feet and a few inches.
All right, so transitioning into our first semester testing. This consisted of putting cassettes that were attached to a air pump around the plasma table. Our hypothesis was that we would see a visible color change in correlation to distance around the plasma cutting machine. And so performing the test, it consisted of 30 minutes runtime and then 30 minutes to let the dust and particulates settle. The cassettes before the test were white color. They're in the upper corner over there. And then you can see the iron oxide changed them to the yellow-orange color, which is pretty cool to look at. We were able to prove that distance directly affects the amount of particulates that are captured in the visibility, because we had a faculty member set the cassettes in order from 1 to 5 based off visibility change, and he was able to do so within 5 seconds. So we were able to conclude that, and going into next semester testing, we're going to send a couple cassettes into a Wisconsin lab to get an actual air quality test result, and then we'll compare those results with the results of the testing when our product is, or our filtration device is in place, and see how it changes.
Going into pressure drop, I don't know if you guys know what pressure drop is, but think of it as resistance of the air moving throughout the system. Every component in a duct, like your duct right here, or any component like filters, has a pressure drop. The main two that supplied a very big pressure drop was our nozzle and then our HEPA filter. That HEPA filter was actually one of the lowest pressure drops we could actually find. So they're normally much bigger than that. And then that flex, it says to be determined. That'll also be one of our bigger ones probably. The reason that is not determined yet is because we want to get the specific material and right kind of thing for our project. And that's kind of tricky to find right now. But I came out to a total of 2.028 inches of water column, or inches of H2O. With that flex duct in, I'm guessing it'll probably be around the 3 to 4 inches of water column, which is actually not too bad for us.
Okay, so with our device, since we're not venting out the air and we're going to recirculate it, one of the interesting aspects was that we're actually going to have some cost savings when it comes to the natural gas. So for our device, it's going to flow at 2400 CFM. And then this number right here, that 0.01, the amount of dollars per pound of steam, is something we got from the AME shop here on campus. And also on the right here, we got the average temps from Brookings, South Dakota over the year. And then we just kind of transitioned it into how much BTUs per hour. Which on the next slide here, we have 10 hours, 20 hours, 30 hours, and 40 hours of runtime for the cutter per week. And then we also have the SDSU plasma cutter, like exact hours we got from Tyler, who's the shop manager here on campus, which was 157 hours. This came out to a whopping $87, which doesn't seem like much, but when you compare it to the cost of the natural gas just in the AME shop, that cost was $360. So adding that extra $88 there would actually be an increase in 22% of the natural gas cost if you were to just vent it out rather than recirculate that air.
So this is a breakdown of our budget. It captures our filters, mechanical components, electrical components, and safety components. And rounding up that total, that brings us to about $7,100. Any questions?
$1,000 for a HEPA filter, how often does that be changed? Or not at all? I'm misunderstanding something.
Shouldn't need to be changed that much, and that is the reason we included that pre-filter, is so that HEPA lasts a very long time, and depending on how many hours he runs it, it should probably be, I would assume, at least a couple years, I would assume. Not specifically sure, but the one you're going to be changing the most is going to be that pre-filter, so that MERV 15. And that's a lot cheaper than that HEPA. It's actually based on pressure drop. So we have, if you've seen on our budget, there's a pressure differential gauge there, and that'll go on both of our filters. And once that, the HEPA never specified what the pressure drop is, but we're going to specify probably to 3 inches. So if you gain 3 inches of pressure drop right there, then you should change it. That MERV 15, I think it said 4 inches of pressure drop, inches of water column pressure drop, and that's when you should change it.
On your design, with your nozzle tracker underneath the table with your change sprocket system, what kind of system did you have to track the head on the plasma cutter?
For that, we have a few options that we want to go with different levels of complexity. One option we thought of initially was using light sensors on the arm of the plasma cutter to track its movement and move our system accordingly with that. We also considered using the G code that is used for the plasma cutter for our system so that they will follow the same system. We also considered putting a tracker on top of the plasma cutting head itself, but we still have to figure out which one works best for that.
Sometimes when you plasma cut stuff, you'll have pieces of metal fall down below, or is that fan ever going to be directly below the cutter?
So that's why we have our nozzle coming from the side rather than directly below it. So that way the slag falls and it's not getting into the fan system then.
Have you been able to select a fan or know where you're getting a fan from that will work with CFM and pressure?
So we have the CFM right there, at 2400. We could select it, but we're going to get that pressure drop. So we have to select our flex duct first. And then after that, we can select our fan. So not too much longer.
On your filter samples, it looks like they were all kind of the same color, kind of a universal color, but I'm assuming you put them at different distances away from the source of the iron oxide. What we expect some to be a deeper orange than others.
So in person, you can easily tell which one was like a deeper orange. Like the 5A and 1A were extremely different. It really gets skewed over a camera because in person it can take you like 5 seconds to put in an order. But the 5A and 1A, those are at like where the user would stand and directly above the cutter, whereas like the 2A and 3A and 4A were at 5, 10, and 15 feet away.
So just could see visibly. I mean,
yeah, you could. Yeah.
Yeah, one of the cool things to go on that was that we actually saw that effect at 15 feet away from the plasma cutter table, which is something to note because when you're looking at overall safety of that entire shop, that means this particulates and fumes could be affecting more than just that corner in that AME shop.
Do you have to worry about having too high capture velocity, like with welding? If you have too much airflow, it messes up your welds. Is that something you're concerned about, or?
Yes, it is, because it could mess up that compressed gas. But since we are going below the table there, it should not, and we will probably not worry about that because it won't be sucking from below. And it'll be 6 inches away also. So it won't be directly below it sucking the fumes down or directly on the side of it. It'll be somewhat offset. Any more questions?
Yeah, looks like we're out of questions, so good job.